In less than 2 years since launching, the James Webb Space Telescope has changed the way we understand the universe. For scientists, the images it's taken offer new possibilities for astrophysics.
Life will find a way. These words couldn't have been more relevant today than ever before in human history. Life has indeed found a way, but not in our solar system. Instead, it is Proxima B that is at the epicenter of the discovery of a lifetime. As the closest exoplanet to our solar system, Proxima B has long captivated researchers and enthusiasts alike, offering a tantalizing glimpse into worlds beyond our own. But this time, it's something really big. The James Webb Space Telescope has detected lights flickering on Proxima B. And what does that tell us? Well, we may have made first contact with an alien civilization. There's a lot to unpack, so let's get started. A closer look at Proxima B and its star. Proxima Centauri has always been a special light in our night sky. It is, after all, the closest star to our solar system. And much like how our Sun has our planet Earth, Proxima Centauri has Proxima B. The star was first identified in 1915 by Scottish astronomer Robert Innes. Located approximately 4.24 light-years from Earth, it belongs to the Alpha Centauri system, which includes the stars Alpha Centauri A and B. Proxima Centauri, however, is a red dwarf, smaller and much cooler than our Sun. This makes it more challenging to observe with the naked eye. Luckily today, we have telescopes that are sensitive to red and infrared wavelengths and can help us take a closer look at the star. Before we get on with the recent discovery regarding Proxima B, let's get some perspective first to understand how any of this is possible. For decades, ground-based telescopes have been essential in studying Proxima Centauri. Observatories worldwide, equipped with powerful telescopes like the Very Large Telescope in Chile, have allowed astronomers to gather important information about this small red dwarf and its planetary companion. Observing from Earth, astronomers have been able to detect flares on Proxima Centauri's surface and measure its luminosity, temperature, and motion within our galaxy. The search for planets orbiting Proxima Centauri began intensively in the early 2000s. Astronomers were piqued by the subtle wobbles in Proxima Centauri's position caused by gravitational interaction with orbiting planets. However, it was only in 2016, after years of study, that astronomers at the European Southern Observatory finally announced the discovery of Proxima B. So how did they do this? They used an analytical technique called the radial velocity method, which observes shifts in the star's light spectrum as it moves slightly due to a planet's gravitational pull. This approach is most effective when used with ground-based telescopes equipped with highly sensitive spectrometers like the high-accuracy radial velocity planet searcher on the La Silla telescope in Chile. Observing Proxima B from Earth-based telescopes, however, has inherent limitations due to atmospheric distortion and light interference. The distance and faintness of Proxima B mean that even the best land-based telescopes struggle to capture its full picture. On top of this, most data collected from Earth-based telescopes rely on indirect measurements, such as tracking Proxima Centauri's movement or measuring spectral shifts, which provide essential but incomplete information. As a result, Earth-based observations were limited to detecting Proxima B's mass, orbital period, and distance from its star, but could not provide detailed information about its atmosphere, surface conditions, or potential biosignatures. This is why we resorted to sending telescopes into space, the James Webb Space Telescope. The James Webb Space Telescope, or JWST, is not only the pinnacle of human accomplishment, but is also a continuation of the exploratory spirit of the space race. The JWST was conceived in the 1990s as a successor to the Hubble Space Telescope. The Hubble Space Telescope, or HST, was launched on April 24, 1990, to peer into the depths of the universe with unprecedented clarity. Hubble was designed to operate in the vacuum of space, free from the distorting effects of Earth's atmosphere. It orbits approximately 547 kilometers above Earth, completing a full orbit every 95 minutes. While doing so, it collects light from distant celestial objects with exceptional clarity, allowing us to visualize them. Hubble has been responsible for numerous groundbreaking discoveries since its launch. For instance, it revealed that the universe is not only expanding, but the rate of expansion is accelerating. In 1995, Hubble took a deep-field image of a small patch of sky, revealing thousands of galaxies in what became known as the Hubble Deep Field. This landmark observation demonstrated the vastness of the universe and the diversity of galaxies. Hubble has also played a crucial role in determining the age of the universe. Thanks to the HST today, we know that the universe is approximately 13.8 billion years old. Hubble's observations have also provided valuable data on the composition and characteristics of exoplanet atmospheres. Moreover, its observations of distant galaxies have allowed astronomers to study the processes of star formation, the interactions between galaxies, and the role of supermassive black holes in galaxy dynamics. Despite the Hubble Space Telescope's monumental contributions, it has inherent limitations. For instance, Hubble is primarily limited to the ultraviolet, visible, and a small portion of near-infrared wavelengths, which prevents it from penetrating the thick dust clouds that often surround nascent stars, distant galaxies, and the cores of active galactic nuclei. Another limitation lies in Hubble's age and technological scope. Launched in 1990, Hubble's hardware and instruments reflect the best available technology of that era. Even with periodic upgrades, some of its equipment is aging and no longer state-of-the-art. Hubble's position in low Earth orbit also poses a disadvantage. While this orbit has facilitated servicing missions, it has subjected Hubble to micro-vibrations, limiting the telescope's imaging precision. Hubble's relatively modest 2.4-meter mirror size further restricts its light-gathering power, limiting its capacity to observe extremely faint, distant objects. These limitations motivated the development of the JWST. NASA, the European Space Agency, and the Canadian Space Agency collaborated on the project, pooling resources and expertise to develop a telescope that could build upon the groundwork laid by Hubble and other observatories. After decades of planning, delays, and budget increases, JWST was finally launched on December 25, 2021. Unlike the Hubble Space Telescope, which orbits Earth, JWST was placed at the second Lagrange point, or LL2, approximately 1.5 million kilometers from Earth, to give it a stable position with minimal interference from Earth's heat and light. Here, the telescope remains shielded from the sun and operates in a constant cold environment, which is necessary for its highly sensitive instruments. Moreover, the JWST can maintain continuous observations without the need for constant adjustments. It is also not affected by atmospheric distortion or light pollution that all land-based telescopes must contend with, allowing for clearer, more detailed images of the universe. This enables astronomers to study phenomena that are invisible or distorted when observed from Earth, including early galaxies, star formation, and planetary atmospheres. JWST's focus on infrared light is especially crucial because, as we look deeper into space, we're actually looking back in time. This is because light from distant galaxies takes billions of years to reach us, showing us these galaxies as they appeared when the universe was much younger. However, as the universe expands, the light traveling through it from distant galaxies is stretched to longer, redder wavelengths. This phenomenon, known as redshift, shifts light from the visible part of the spectrum to the infrared. By focusing on the infrared spectrum, JWST can capture light from these early galaxies that Hubble could never detect. The JWST's ability to perform cosmic reconnaissance is noteworthy, as it can detect and analyze exoplanets, study their atmospheres, and provide clues to whether these planets could host life. All of this is made possible by its impressive design. Central to this design is the primary mirror, which spans 6.5 meters in diameter and is composed of 18 hexagonal segments made of ultra-lightweight beryllium and coated with a thin layer of gold to optimize infrared reflectivity. This large mirror allows JWST to collect significantly more light than Hubble, enhancing its sensitivity and enabling it to observe fainter and more distant objects. Another critical component is the 5-layer sunshield, which protects the telescope from sunlight and keeps its instruments at the necessary cold temperature. Each layer of the sun shield is made from a specialized material called captan, coated with aluminum to reflect heat. This shield allows JWST's instruments to remain at temperatures near -233 degrees Celsius and detect faint infrared signals without interference. JWST houses 4 main scientific instruments, each with specialized capabilities. The near-infrared camera, or NIRCam, captures images in the near-infrared spectrum, allowing us to observe the formation of stars and galaxies. The near-infrared spectrograph, or NIR-SPEC, analyzes light from up to 100 objects simultaneously, determining their chemical composition and age. The mid-infrared instrument, or MIRI, extends JWST's vision into the mid-infrared, allowing for detailed studies of distant galaxies, exoplanet atmospheres, and cool objects like brown dwarfs. Finally, the near-infrared imager and slitless spectrograph, or NIRIS, ensures accurate pointing and can study exoplanet atmospheres. JWST's infrared capabilities are crucial for detecting possible biosignatures. It also allows us to understand the processes that may lead to habitable conditions in distant planetary systems. By examining exoplanet atmospheres, JWST identifies molecules like water vapor, methane, and carbon dioxide, which are potential indicators of biological processes. Such discoveries have profound implications for the search for extraterrestrial life. The James Webb Space Telescope embodies humanity's collective efforts to understand the cosmos. It is uniquely suited to peer into the distant universe, probing the mysteries of star formation, galactic evolution, and the conditions that might support life beyond Earth. By focusing its attention on worlds like Proxima B, JWST expands the boundaries of human knowledge and inspires future generations to explore. Speaking of Proxima B, let's see what we're dealing with. Proxima B, the planet that could be the second Earth. Proxima B is to the red dwarf star Proxima Centauri as our planet Earth is to our Sun. Located a little over 4 light-years from Earth, it is the closest known exoplanet to our solar system. Its proximity to our home offers an unprecedented opportunity to study the environmental and atmospheric conditions that may support the development of life. Proxima B resides within the habitable zone, also known as the Goldilocks zone, around Proxima Centauri. This is a region where conditions are just right for liquid water to exist on a planet's surface, which is essential for life as we know it. The habitable zone allows for a stable climate that can support diverse ecosystems, making Proxima B a prime candidate for astrobiological studies. A fascinating aspect of Proxima B is that it is a tidally locked planet. This means that one side of the planet constantly faces its star, experiencing perpetual daylight, while the other side remains shrouded in darkness. This creates a drastically different environment from what we experience on Earth. Earth rotates on its axis, which gives all parts of the planet a cycle of day and night. This rotation is key to our climate, weather patterns, and the general habitability of our world. The alternating exposure to sunlight ensures an even distribution of heat, moderates global temperatures, and drives the dynamic atmospheric systems that create winds, clouds, and seasonal changes. This variation between day and night allows for diverse ecosystems, fostering life as we know it. On Proxima B, however, one hemisphere is locked in constant sunlight while the other exists in eternal night. The side facing Proxima Centauri would be exposed to constant, intense radiation from its red dwarf star, likely creating extremely high temperatures and a barren landscape due to solar bombardment. Meanwhile, the dark side, in perpetual shadow, would experience freezing temperatures, perhaps plunging to extremes that would inhibit most known forms of life from thriving. This stark contrast likely creates a thin, habitable twilight zone along the planet's terminator line, which is the border where day meets night. In this zone, conditions may be moderate enough for life to exist. These conditions would lead to very different atmospheric and weather patterns compared to Earth's. Strong winds may surge from the hot side toward the cold side as heated air rushes to equalize the temperature difference across the planet. If Proxima B has an atmosphere, it would play a crucial role in redistributing heat, potentially making life possible within the twilight zone by buffering temperature extremes. But before we move on to the habitability of Proxima B, let's pause a little and take a look at the bigger picture. Are there aliens out there? This question is one of the most profound and enduring in human history. Not because it is impossible to answer, despite the many difficulties, but because of the potential ramifications of the answer. Today, scientific advancements place us closer than ever to potentially spotting alien life. But the journey to this point has been long, complex, and filled with fascinating twists. Let's start with the basics. At its most basic, life as we know it requires three main elements: liquid water, an energy source, and a complex chemistry that enables growth and reproduction. On Earth, these requirements are met through water-based biochemistry, powered by sunlight, or in some cases chemical energy from minerals. But as we've learned through the study of extremophiles, which are organisms that thrive in extreme conditions on Earth, the requirements for life may be more flexible than we previously thought. For example, some extremophiles survive without sunlight in highly acidic environments or in the intense pressures and temperatures of deep-sea hydrothermal vents. This suggests that life could exist under a broader range of conditions than initially assumed. Astrobiologists now believe that these fundamental requirements could be met in various places within our own solar system, such as in the subsurface oceans of Jupiter's moon Europa or Saturn's moon Enceladus. The discovery of thousands of exoplanets in the habitable zones of their stars also opens the possibility that life could be widespread across the galaxy. But if life could indeed be elsewhere, why haven't we seen it yet? This puzzling paradox entrenched itself in the mind of physicist Enrico Fermi, who famously asked, "Where is everybody?" He was not mistaken in asking this question. After all, given the vastness of the universe, the number of stars, and the likelihood of habitable planets, we should have already detected signs of intelligent alien civilizations. So where is everybody indeed? This is what we today call the Fermi paradox, and experts have presented a wide range of potential explanations to address the question. Some scientists suggest that intelligent civilizations may be exceedingly rare or short-lived, perhaps because of technological self-destruction. Just look at us. It hasn't even been a century since we first developed nuclear weapons, and we've been living in fear of a nuclear holocaust ever since. Could this have happened to other advanced alien civilizations? But wait, there's more. Some experts propose that advanced civilizations are out there, but choose not to communicate with us, or that they are using forms of communication we don't yet understand. Or maybe it's none of these. Maybe we're the most advanced civilization in the cosmos, and thus are destined to make first contact with the aliens. It could just as easily be the other way around, and we might find ourselves visited by something so intelligent and advanced that we may not be more than guinea pigs for them. Some even believe that life as we know it on Earth might not be from here itself. According to panspermia theory, life, or at least the building blocks for it, might be able to travel across space, carried by meteorites, comets, or even microscopic particles that survive interstellar travel. In this view, life on Earth may have been seeded by microorganisms or organic compounds that originated elsewhere in the galaxy. This idea is not as far-fetched as it might seem. Researchers have discovered amino acids, the building blocks of proteins, on meteorites, and there is evidence that some microorganisms can survive the harsh conditions of space. In 2014, the European Space Agency's Rosetta mission detected complex organic molecules on the comet 67P/Churyumov-Gerasimenko. If panspermia is correct, it would mean that life might be more interconnected across the universe than previously thought. Some scientists are so convinced by the idea that they took a step further and proposed the direct panspermia theory. Proponents of this theory claim that life didn't just accidentally spread across the universe via natural processes, but was, in fact, intentionally transported. They claim that an advanced alien society may have intentionally sent microorganisms or genetic material to other planets, possibly using specialized probes or spacecraft designed to carry these seeds of life. They may have done so to spread life across the galaxy or to safeguard life against extinction on their home planet. By seeding multiple worlds with life forms or even DNA, this civilization would essentially create a network of planets with the potential for life to evolve and adapt in varied environments. If life on Earth did indeed arrive from a distant world through intentional transmission, it would explain certain mysteries in the origins of life. For example, life on Earth began relatively quickly after the planet became habitable, which some scientists find surprisingly efficient given the complexity of life. The idea suggests that life might not have started from scratch here, but instead, Earth could have been seeded with pre-existing life forms that had already overcome the early hurdles of evolution elsewhere. If true, direct panspermia raises ethical and scientific questions about our own exploration of the cosmos. Some scientists suggest that if we ever develop the technology to seed distant, lifeless worlds, we could follow in the footsteps of these extraterrestrial civilizations, carrying life beyond Earth to perpetuate it across the galaxy. Similarly, if life exists elsewhere, humanity's next big step would be to make contact. This quest has driven much of modern astronomy and space exploration. One of the most well-known efforts is the Search for Extraterrestrial Intelligence, or SETI, a project that began in earnest in the 1960s. SETI scientists use radio telescopes to scan the sky for signals from intelligent civilizations, looking for patterns that cannot be explained by natural sources. While SETI has yet to find definitive proof of alien life, the search has led to valuable advancements in signal processing and deep space observation. In recent years, private foundations such as Breakthrough Listen have joined the effort, bringing more resources to the table. The quest for contact with alien civilizations reached a significant milestone in 1977 with the launch of the Voyager 1 and Voyager 2 probes, which now travel through interstellar space. These spacecraft carry with them the famous golden records, phonograph records containing sounds and images chosen to portray the diversity of life and culture on Earth. Designed by a team led by Carl Sagan, the golden records were intended as a message in a bottle for any extraterrestrial civilization that might find them, conveying greetings in multiple languages, music from different cultures, and images depicting human life and natural phenomena. While the Voyagers are unlikely to encounter alien life anytime soon, they represent humanity's first intentional attempt to communicate with other civilizations. One of the closest targets in the search for extraterrestrial life has been Mars. With evidence of ancient rivers, lakes, and potentially even oceans, Mars once had conditions that may have supported life. However, due to changes in the planet's climate, including the loss of its atmosphere and magnetic field, Mars is now an inhospitable desert. Scientists have found signs of organic molecules on Mars and seasonal fluctuations of methane gas, which may be produced by biological processes. But if life ever existed on Mars, it may have long since died out, leaving only faint traces. The search for past life on Mars continues with missions like NASA's Perseverance rover, which has stored several rock and sediment samples since early 2021. These samples will help scientists analyze Mars's environment from billions of years ago, potentially offering clues to whether microbial life could have once existed there. However, we need to study these samples first, back on Earth. To make this possible, NASA and the European Space Agency are collaborating on the Mars Sample Return, or MSR mission. This effort, still in development and tentatively expected to launch by the early 2030s, would involve sending spacecraft to collect the cached samples and return them for detailed analysis on Earth. As our technology advances, so too does our ability to search for extraterrestrial life. The James Webb Space Telescope has begun observing distant exoplanets, analyzing their atmospheres for potential biosignatures. Additionally, next-generation observatories, like the European Extremely Large Telescope and the Square Kilometre Array, will offer unprecedented sensitivity, potentially detecting faint signals from distant worlds. The discovery of thousands of exoplanets has transformed our understanding of the cosmos, revealing that planetary systems are the norm rather than the exception. Some of these exoplanets, located in the habitable zones of their stars, have atmospheres and conditions that could support life. Governments, private foundations, and space agencies are investing billions of dollars in this quest because the implications of discovering extraterrestrial life, especially intelligent life, would be staggering. Moreover, the search for alien life is more than a scientific endeavor. It is an expression of humanity's fundamental curiosity and our desire to understand our place in the universe. Finding extraterrestrial life, even in microbial form, would show that Earth is not unique and that life has the potential to arise in multiple places across the cosmos. In many ways, the search for alien life is a continuation of humanity's age-old quest to explore the unknown, to seek out new horizons, and to reach beyond what is familiar. But these efforts are not without their challenges. Studying Proxima B, for instance, is no walk in the park. Challenges from Proxima Centauri. While Proxima B is suitable for hosting life in many ways, its star does introduce some complications. As an M-dwarf or red dwarf star, Proxima Centauri is very different from our own Sun. For instance, it is cooler, smaller, and prone to intense solar flares. These properties have significant implications for Proxima B, particularly when it comes to the planet's atmosphere and the viability of any life that might exist there. Proxima B orbits Proxima Centauri at just 0.05 astronomical units, which is about 1/20th the distance from the Sun to Earth, or roughly 7 times closer than Mercury is to the Sun. Moreover, as noted earlier, Proxima Centauri is prone to frequent and intense solar flares, which are sudden eruptions of energy from the star's surface. These flares are not just more frequent than those of our Sun, but also disproportionately powerful relative to the star's size and mass. Proxima Centauri can produce superflares with energy levels thousands of times greater than the strongest flares recorded on the Sun. Such flares emit high levels of X-rays and ultraviolet radiation, creating a harsh environment for any orbiting planets. For Proxima B, the proximity to its parent star makes these solar flares and accompanying radiation particularly dangerous. Any atmosphere that Proxima B might have could be severely impacted by this radiation. Simulations indicate that the high-energy particles from these frequent flares can strip away a planet's atmosphere over time. Proxima B, if it initially had an Earth-like atmosphere, may have lost much of it due to this intense stellar activity, especially if the planet lacks a strong magnetic field to deflect charged particles. Without a protective atmosphere, surface temperatures would fluctuate wildly, and harmful radiation would bombard any exposed surfaces, posing significant risks for any potential life forms. Continuous exposure to high-energy radiation is also likely to degrade organic molecules, the building blocks of life. For instance, ultraviolet radiation can break molecular bonds, which may prevent complex molecules like amino acids and nucleotides from forming or surviving long enough to support life. This radiation-induced molecular breakdown challenges traditional concepts of habitability, suggesting that if life exists on Proxima B, it would need extraordinary resilience or alternative biochemistry to endure such conditions. In addition to the immediate impact of solar flares, prolonged exposure to high levels of radiation has more insidious effects on Proxima B. Unlike on Earth, where most harmful UV and X-ray radiation is filtered out by the ozone layer, Proxima B's atmosphere may not provide the same level of protection if it has any atmosphere left at all. If any life exists on Proxima B, it would likely need to be extremely resilient to radiation. On Earth, certain microorganisms, such as Deinococcus radiodurans, can survive high doses of radiation, including UV and X-rays. Life on Proxima B might similarly evolve with extreme radiation resistance, perhaps by staying deep within the planet's crust, where radiation exposure is minimized. Alternatively, if there are subsurface oceans, as theorized for icy moons like Europa in our solar system, life could thrive there, shielded from radiation by layers of rock or ice. Another possibility is that Proxima B hosts life forms that have developed unique biochemical adaptations. For instance, they might have evolved highly efficient DNA repair mechanisms or alternative genetic structures that are less vulnerable to radiation-induced damage. Alternatively, they might not rely on DNA or RNA at all, instead using a different molecular basis for heredity and cellular function that we cannot yet imagine. What we do know for sure is that if we ever attempt to explore Proxima B, whether with robotic probes or human missions, the radiation environment will pose a serious challenge. Any human presence would likely need to be located in the terminator region, where conditions might be more moderate. But all of this is conjecture for now. Or is it? Well, as it turns out, there is good reason for us to believe that Proxima B hosts life. Potential for life on Proxima B. The James Webb Space Telescope recently observed Proxima B, marking the clearest view of the exoplanet to date. Due to JWST's advanced infrared capabilities, astronomers can now analyze faint signatures of life on this distant land. But how did the JWST do it? Well, when light from a distant planet passes through its atmosphere or reflects off its surface, astronomers can separate it into various wavelengths and study the unique fingerprint it leaves. This method, known as spectrography, allows scientists to identify molecules like water vapor, carbon dioxide, methane, and even oxygen. On Earth, these molecules are associated with life, and their presence on Proxima B could suggest similar biological processes. So, what did we find on Proxima B? The case for life on Proxima B is compelling despite its harsh environment. Its position within the habitable zone around Proxima Centauri suggests that it could sustain liquid water, if not on the surface, then at least underground. While its star is highly active, emitting intense flares and radiation, it's plausible that life forms could adapt similarly to extremophiles on Earth, which thrive in high radiation zones. Additionally, Proxima B's tidally locked nature, where one hemisphere faces perpetual daylight and the other darkness, creates a temperate terminator line between day and night, where moderate conditions could support life. However, scientists are not relying on this information alone. They have already taken the next step. JWST and other telescopes are focusing on Proxima B to detect the red edge, which is an intriguing biosignature when assessing the potential for plant-like life on exoplanets such as Proxima B. On Earth, vegetation strongly absorbs visible light for photosynthesis, but reflects infrared light, creating a distinct red edge when viewed in the infrared spectrum. This unique spectral signature could, in theory, be detected on Proxima B if plant-like organisms adapted to its environment were present. Proxima B does receive a lot of infrared radiation. If life has adapted to harness this energy, it might develop photosynthetic processes optimized for infrared light, potentially leaving a similar red edge signature. If we were to detect this, there would be no further doubt. Considering the extremities on Proxima B, life might dwell beneath the surface, shielded from the harshest conditions. If the planet has an atmosphere capable of diffusing light, photosynthetic life could still exist, though it would likely be adapted to low-light conditions. On Earth, cyanobacteria found in polar regions or deep ocean areas have evolved to photosynthesize in very low light, which might be similar to what organisms on Proxima B would need. Alternatively, life on Proxima B might rely on bioluminescence or a unique form of energy generation to sustain itself in low or intermittent light conditions. Radiation resistance would also be essential. Life forms might have robust DNA repair mechanisms or employ biological processes that mitigate radiation-induced damage. Whatever the case, the search for life on Proxima B isn't just about finding other living organisms. It's part of humanity's broader quest to understand our place in the cosmos. For millennia, people have looked up at the stars and wondered if we are alone. The discovery of planets like Proxima B brings us closer to answering this age-old question, suggesting that life might be more versatile and widespread than we previously believed. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.